So first of all, thank you, Wanning, for your introduction, and especially it's already very late in China. And thank you all for being here. And it is really my great pleasure and honor to speak here today at Bench 2022 to talk about some of our recent research on fair machine learning with imperfect information. Okay, and feel free to ask questions if you have any. And I will just also have the opportunity to answer the question at the end. Okay, so first of all, as many of you know that in the last decade, AI and machine learning models have demonstrated great achievements and empowered many aspects of human lives, such as news recommendation, news ranking, and autonomous vehicles, information sharing, and so on and so forth. However, recent research showed that a learned AI or machine learning model can have bias against specific demographic groups, such as gender, race, religious status, so on and so forth. And this is actually a very critical concern in these high-stake applications, such as filtering the loan applications and algorithm justice, and credit card approval, and so on. There are some examples I show here. For example, this report shows that the schools using software to filter these student applications may be biased towards specific racial groups. And a tool for crime prediction called Compass has been shown to be biased and is more likely to assign a high risk score for African-American offenders. So in computer vision domain, as you can see on this bottom left, a face recognition tool can also be biased and maybe over predicting Asians as blinking. So as you can see from these examples, bias in machine learning can come from different sources, such as this underrepresented data or incomplete training data sometimes. And bias can also come from algorithm design without considering fairness criteria, right? Or even they can come from user interactions, such as user behavior data. So we can see that it is becoming increasingly important to study the problem of mitigating bias and ensure fairness in machine learning models. Okay. To do so, to ensure fairness in machine learning models, recent advancement in fairness-aware machine learning aim to optimize different fairness measures, including individual fairness and group fairness. So what is individual fairness and group fairness, right? Commonly, definition of individual fairness is, to try to give similar predictions to similar individuals in the data set. Such as counterfactual fairness or fairness through awareness. These are commonly used approach. And group fairness is to treat different groups equally, like using these statistical measures like statistical parity or called demographic parity and equalized odds, as I shown here on this table. And the current fair machine learning algorithms can also be categorized into three types according to at which training stage this fairness criteria is enforced, including pre-processing fairness algorithm, in-processing fairness algorithm, and post-processing. In general speaking, pre-processing algorithms are applied before the training even happened. So basically, they try to apply some criteria to transform the original data into some new form such that the inherent bias in this data set is mitigated. And in processing algorithm, fairness algorithm basically try to proactively or explicitly incorporate some fairness constraint when build these machine learning models, such as adversarial debiasing and readjusted removal. Okay, and post-processing, algorithm basically tries to work on the prediction result by using some novel techniques to kind of transform the prediction result into some new form such that the bias is mitigated. So basically, this is all existing approaches, and there are a lot of recent efforts try to work on this problem in machine learning and AI area, and it's a really important issue. But the majority of these aforementioned fairness models, they, you should assume that there is enough training data available. However, in the real world scenario, sensitive attributes such as age, such as race, gender, they are often limited and even unavailable due to privacy, legal or other regulation constraints, right? So this, in addition to that, sensitive attributes can also be noisy or manipulated in some ways. Because, for example, this survey participants may, be incentivized to obfuscate or hide their real sensitive attribute information because they have concern about privacy. Okay, so in this talk, I will just briefly introduce some of my recent work on tackling these impervasive challenges when we try to build fair machine learning models with this imperfect information. And specifically, I will talk about estimation challenge, adaptation challenge, and denoising challenge. So next, I will introduce some representative research in our group on fair machine learning for solving these challenges. So first of all, if there are no sensitive attributes available or collected, how can we ensure fairness classification result with what we call related attributes? Okay. Second, to build fair machine learning models in one domain which may not have sensitive attributes, can we leverage the rich information from an existing domain to help? Third, user-sensitive attributes can be noisy because of this privacy protecting mechanism. So can we achieve fair classification when most of the sensitive attributes, they are private? Okay. So next, I will start with the first work, introduce how we can leverage related features to learn fair classification models, which was published in Wisdom 2022. So, since these sensitive attributes, they're unknown and not available. So our idea is to explore auxiliary information to estimate these sensitive attributes. And then we can use these sensitive attributes to build fair models. And, prior knowledge shows that these related attributes can be strongly correlated with sensitive attributes. So what do we mean by related attributes? So one example here I show here is from existing social theory studies showing that this marital status is strongly related to gender. So if we don't have the information of gender, then probably we can use marital status and other related attributes to approximate and estimate the sensitive attributes. So that's the idea here. So essentially in this paper, we want to answer these two research questions. First of all is, would related attributes be useful to estimate sensitive attributes as an auxiliary information? And how to model related attributes to help build fairness classification models. Okay. So to do so, basically the objective of our framework is to build an effective model that leverages multiple related attributes for fair classification. The challenge is these signals from different related attributes, they may not equally contribute to the inference of the sensitive attribute. So in this framework, we propose to jointly learn, this representation from the data set, including the normal attributes and the related attributes for fair classification. And as you can see, basically our framework consists of these two components. The first one is a prediction error of all the samples with this cross entropy loss to optimize the prediction accuracy. And the second module is this fairness module, where we try to build a regularization term to enforce the independence between the related attributes and the predicted labels to ensure this fairness. And we also incorporate this parameter lambda to regularize the importance of each related attributes towards the final prediction of our framework. Okay. So in these experiments, we have shown and compared several state-of-the-art methods, including the fair classification methods on different widely used real-world data sets. And we observed that the proposed framework can achieve a better fairness performance measured by equal opportunity and the demographic parity, which are commonly used in fair machine learning community on different data sets. And we also show that comparing with other baselines that didn't use the sensitive attributes, our model can get better performance, which shows that it can better leverage related attributes to do the fair classification task. And we also perform some analysis to check whether our model can really automatically learn the importance of each source of the related attributes by looking at these parameters lambda, and then basically we can see that it matches our expectation of how the real world knowledge from social science has informed, right? For example, here, as you can see on this adult data set, we have plotted this lambda for each of the related attributes like age, work class, relation, and education. And then age, because it's a strong indicator for the sensitive attribute in this adult data set. So it, at the end, this lambda has a bigger value to indicate this, the learning process is relatively matching this real world case. So, to summarize this work, basically, we studied this new problem and challenging problem to build a fair classification models with unknown sensitive attributes. And we show that, using related attributes, related features is helpful. And we propose this framework can, jointly learn this, related attributes and the original normal attributes together for the fair classification tasks. And we also show that different related attributes, they contain complementary information in this paper. Okay. So any questions for now before I move to the next paper? Let me check if there are any. No? Okay. So, let's go to the next. So the next piece of work we are working on is to study a fair machine learning model in a domain that has no sensitive attributes, and then how can we leverage a related domain that has rich information to help us to build a effective fair models in the current domain. Okay. So next, I will introduce this paper on fair classification while domain adaptation. So the problem is, since we lack the sensitive attributes for training a fair model in this target domain, I will give an example of what we mean by target domain in this figure shortly. Then our idea is try to look for some other related domains and try to, adapt knowledge from that domain and help us to build a fair models. Okay. So as I shown here in this example, basically this is a kind of cross-domain fair classification scenario for assessing the credit card approval. And as you can see from this figure that in the source domain, which is on the left, is more like a mature market with a lot of information collected from the customers, but the target domain is a new market we try to launch, and the sensitive information is unknown in the target domain. Okay, so essentially we aim to answer these two questions. First one is how we can estimate the sensitive attributes in the target domain by adapting the knowledge from the source, and then how we can ensure an accurate and fair prediction in the target domain. Okay. So to this end, we built this model called FairDA. essentially this model contains two adversarial learning approach. That's why we call it the dual adversarial approach. And the first component is this adversarial domain adaptation module. And the goal is really to estimate the sensitive attributes for the target domain by optimizing this loss function L1. So L1, as you can see, includes basically two loss function LA and LD. LA is to ensure the prediction of the sensitive attribute in the source, and LD is to do the domain adaptation here. Okay, and the second adversarial component is to ensure the fairness in the prediction of the target domain, and as shown here with this loss function L2, and similarly, L2 contains a objective function to optimize Ly by minimize the prediction error, and LA to ensure the non-dependence between the sensitive attributes and the prediction label to ensure fairness. Okay, so at the end, the overall loss function is to minimize the combination of L1 and L2 using this minimax objective function. And then we already have this paper put in archive and it's under review right now. And if you are interested, please check the preprint for more details. And we have done some experiments as well. And then we compare this method called FairDA with existing fairness models. And we, through this table on the right, you can see that FairDA can achieve a better fairness performance in terms of delta GP, which is the demographic parity, and equalized odds compared to existing baselines. And on the bottom of this table, we show that how each of these adversarial learning components contribute to this framework. So we have done this ablation study, and we show that each of these adversarial learning, it is contributing to the final fairness result significantly. Okay. And by the way, we also done a theoretical analysis in addition to these empirical studies in the paper. So not only showing this in this real world data set, it has better performance, but also we have provided theoretical guarantee in this paper. And if you're interested, you can check. So basically, to summarize this paper, we studied this new problem of fair classification with domain adaptation. And we proposed a framework, FairDA, that can transfer the sensitive attribute information from a similar domain and can help to achieve a better fair classification results in the target domain. And this model is effective on jointly transferring the sensitive attribute information and also ensure the fairness performance with this dual adversarial learning framework. Okay. So our next piece of work is try to look at the scenario that when the user sensitive attributes, they are already, privacy protected. And in this case, we want to ask, how can we achieve fair classification when most of the sensitive attributes, they are private? So next, I will introduce this work on fair classification with semi-private sensitive attributes. So, in AI machine learning, privacy and fairness are two important research direction and problem. And ensure both privacy and fairness is important, right? And if you think about it, is there some text chat? No? Okay, there's a question, but I will probably answer at the end if that's okay. So I just realized in the chat. So basically, right. So in this work, what we are trying to do is we assume that we can only collect private data. To be more specifically, the data with private sensitive attributes. And we want to build a fair machine learning model on top of this private data. Okay. And So the question here we're trying to answer is how can we make fair prediction with private data? It turns out, if we assume that all of these sensitive attributes, they are private, it probably is more challenging to solve. And in the real world case, actually, it is possible. Sometimes it is possible that some of the users they are willing to share their sensitive attribute information, but most of them still they are very cautious about that. And based on this, we study a new setting or more practical setting that we call the semi-private setting. Essentially, what we do is we assume that, as you can see on the right side of this figure, we assume that of all these data points, most of these sensitive attributes, they are private and they are basically noisy in a sense, but still we can get access to a limited number of reliable sensitive attributes. As you can see on the right side, we have these two data points that contain the sensitive attribute information, but most of these other user sensitive attribute information, they are private. And this is a real world case. It can be done by applying, for example, this widely used the differential privacy algorithm, right? Such as deep differential privacy and local differential privacy, okay? So just want to clarify that now we have this data set on the right side. Can we still achieve fairness? That's what we want to do here. So we propose a framework called FairSP to deal with this semi-private setting. Okay. Sorry. So FairSP, tries to first correct those sensitive attributes, because those private sensitive attributes, they're essentially noisy, right? And our idea is to first try to correct these noisy sensitive attributes, and then utilize the original limited amount of reliable sensitive attributes and combine with these corrected sensitive attributes to do the debiasing. Okay, so that's the idea here. And as you can see from this figure and this objective function, we have these two terms. First term is LY, is basically a standard cross entropy loss to ensure the prediction accuracy of the labels. And the second term is an adversarial debiasing loss on both the clean and corrected data. But how we can correct these sensitive attributes, we actually draw from some of the research on weakly supervised learning, try to learn the distribution among private attributes and clean attributes to better correct those private attributes. And again, the detail will be in this preprint online, so you can check later, okay? So we have done some experiments to evaluate whether this model can still achieve fairness with these private, mostly private sensitive attributes. And we compared our methods, which is the very end, FairSP, with several other baselines in different data sets. And essentially, we can see that FairSP can have a best fair performance in this setting, and with very comparable prediction performance, right? And essentially, it's always a trade-off between fairness and prediction in principle, but still, we show that FairSP can achieve better fairness performance without losing a lot of prediction accuracy, okay? So, okay, I will see this question, but I will answer shortly, okay, after this. So, and we also have done some experiments to check under different privacy constraint, how is our model performing compared with existing methods. On the left figure, it is to show that under different privacy budget. So privacy budget is basically a term in this local differential privacy. Essentially, if the privacy budget is large, it means that it is less private. Okay, and as you can see that on the different privacy budget, our method, which is showing this green line, has consistently lower this delta EO. Basically, delta EO is equalized odds. The smaller the value, the better the fairness performance. So we can see that it consistently has a better fairness performance comparing with the baseline. And on the right side, it is to show that because in our training data, we have a small amount of clean sensitive attributes. So like how our method perform with the different clean ratio. So with a higher clean ratio, it means that we have a larger number of instances with sensitive attribute available. So as we can see from this table, that this figure, that with different clean ratio, our method can consistently achieve a lower delta EO, indicating a better fairness performance. Okay. So to summarize this work, we studied this problem of fair classification with semi-private sensitive attribute setting, and we propose this framework FairSP, which can simultaneously derive a corrected sensitive attributes from private ones, and further learn a fair classifier with adversarial learning on both clean and corrected data. And we show that FairSP can achieve higher fairness performance compared with other baselines. Okay. So now I have introduced 3 representative work in our group to show you that how we can learn fair machine learning models with imperfect information to solve this estimation challenge, adaptation challenge, and the denoising challenge. Okay, so next I will briefly talk about some open research directions along this line. First of all, fairness machine learning with imperfect information is a challenging issue because this imperfect information is often the real world case, but how to leverage imperfect information is really challenging because, we really want to extract knowledge from this imperfect information, and this knowledge can help us to improve our model performance, right? But it is not easy to do that. And second is, data is very important. In many of these machine learning and AI studies, and in this case, it's very often impractical and difficult to collect data with reliable sensitive attributes because of the reasons we mentioned, right? Like privacy and regulation issues here. So how can we still learn fair models with this imperfect data? And third is, fairness and utility is often a trade-off, but if we only rely on this data-driven approach, it can be limited. That's why in this second piece of work, in the first piece of work, we try to learn from existing social science studies to narrow down a set of related attributes that we can leverage to infer or estimate the sensitive attributes. Okay. And it's also important to develop like robust fairness machine learning models, because many of this data can be manipulated, and we need to design, proactively design some attacks on these fair models, and eventually try to defend such kind of attacks and design fair models with adversarial information. And also nowadays, people are talking about responsible AI or trustworthy AI machine learning, talking about this fairness, privacy, explainability issues. And there are a lot of great work along each of this line of research, but essentially they are inherently related, and there are some recent trends to think about how or whether it's possible to unify these different research together and propose some benchmarking framework that can further advance the research of this responsible AI and trustworthy AI, right? So one example is, when we talk about explanation, can we ensure the fairness in these different kinds of expandable models, right? And also when we talk about explanation, can we, achieve or derive explanation with still privacy protected? So all of these are very important and emerging research questions that are understudied and being should be further explored by the community. Okay. So that would be my talk for today. And first of all, thank you for the bench committee for the invitation. And I would like to thank my lab members and collaborators. And currently, I'm also looking for highly motivated PhD students to work on machine learning, data mining, and NLP. So thank you all, and looking forward to your discussion and future collaborations. Thank you.